Welcome to the video for Chapter 9, Capacitance. We're going to talk a lot about different types of capacitors today. We're going to talk about intentional capacitors, which are typically designed with two parallel conductive plates. We're also going to talk about unintentional or parasitic capacitances. You probably can easily remember or look up the equation for calculating the capacitance of two parallel plates, but we're going to see how you can derive not only that one, but also the capacitance of any object. Every object has capacitance. Your laptop computer has capacitance. Any piece of metal that you pick up has capacitance. Your shoe has capacitance. So we're going to see how to calculate that capacitance given strictly the geometry and the materials that are used to comprise that object. We're also going to talk about the breakdown voltage. What causes an insulator to fail? What causes an insulator to effectively become a conductor? And how can we calculate the voltage at which that's going to happen? And then we're going to talk about electrolytic capacitors. It turns out that electrolytic capacitors are special. They're special in a couple of ways, one of which is good and one of which adds extra challenge. We're going to understand how it's special in those two ways. So let's talk a little bit about the first practical capacitor, the Leyden jar. The Leyden jar was invented or developed in 1745. It was actually discovered accidentally because a person had a little metal medicine jar in his pocket and happened to touch it against something that had a lot of positive electrostatic charge, and later was shocked by it and realized that he could store electrical charge in this metal jar and needed to understand why that was. The Leyden jar, as it was originally developed at the University of Leiden in Holland, could store up to 35,000 volts of electricity. And kind of a sad story, several of the people who did early experiments with Leyden jars actually received some pretty severe electrical shocks. Fortunately, none of them were fatal, but you can imagine if you're working with something that has 35,000 volts and you don't know that and you don't understand the concept of a capacitor, you can imagine that could cause some pretty severe damage. So we're going to talk a little bit about capacitors today. We're going to talk a lot about how if you move positive charge into a region, it makes it more difficult for future positive charges to enter that region. And yes, it's also true for negative charges. I'm going to talk mainly about positive charges just to try to keep things as simple as possible, but know that the same thing, of course, is true if you moved a negative charge into a region. So what we know is that if I move a positive charge into the region, it will repel other positive charges. It will therefore make it require more potential energy for other positive charges to move into that region, and therefore it's going to increase the voltage. So moving a charge into a region increases the voltage in that region. So what we see then is that if Q increases, then the voltage is also going to increase. And the question is, by how much does the voltage increase? And the answer to that is found in capacitance. So the relationship between voltage and the charge that induces that voltage is typically linear. And when I say typically, for this introductory course, it's always linear. And so we can calculate the capacitance as simply the ratio of charge divided by the voltage. Now, we know that charge, Q, is in units of Coulomb. Voltage, of course, is in units of volts. So the units here are Coulomb per volt. This is equivalent to a farad. So the units of this are a farad, but a farad is a very large unit of capacitance. In the same way that a coulomb is a very large amount of charge, we know that the coulomb here is large, and so therefore the farad here is also going to be large. So typically when we're working with a capacitor, it will be in units of picofarads or nanofarads, or in the case primarily of electrolytic capacitors, microfarads. Now, the most important and commonly used type of capacitor is a parallel plate capacitor, which is, as you can see in figure 9.1, composed of two flat metal surfaces that are parallel to each other, and there's an electrical lead connecting the two of them. When a voltage differential is placed between these two plates, which might, for example, be if we attach the bottom plate to ground, and maybe we have a voltage supply over here, plus to minus, and then that's going to come in and connect to the top plate. Maybe this is, say, 10 volts, or it could be 14 volts, or whatever it is. That's how we're going to induce a voltage difference V sub AB across these two plates. We can see that the surface area of each of the plates is listed as A, and that as we are causing this current to flow, because remember that this is going to cause a current to flow in this loop, as that current is flowing in, positive charges are going to accumulate on the top plate, and positive charges are going to move away from the bottom plate, which leaves behind a negative charge. So we get plus Q on the top plate minus Q on the bottom plate. We're going to assume for now that the space between the plates is empty or filled with a vacuum. At the end, we're going to say, oh yeah, what if it were a dielectric? And it's a pretty simple improvement to the equation. Now the side view of the parallel plate capacitor is shown here, and the most important thing that I want you to see is that because there are positive charges on the top plate and a net negative charge on the bottom plate, the electric field lines are pointing straight down from the positive charges to the negative charges. Now we're assuming here that this is an infinitely large parallel plate capacitor. Obviously we can't follow through with that. There is no such thing as an infinitely large parallel plate capacitor, but if it is very large, and I'll sort of draw this as an extreme, it's not an extreme. I'll draw this as a representative example. If you're in the middle of this region, it does look as though it's infinite. And as we work our way toward the edges, it doesn't look quite as infinite as it used to. So those electric field lines are going to begin to curve as we get toward the edges, and the curving becomes more extreme as you get out toward those edges. So while I've shown those lines being totally parallel in the figure 9.2, be aware that if the surface area is not infinite, then there is some bending, or some fringing we call it. And so fringing of those fields near the edges is going to change the capacitance calculation just a little bit, but we're going to assume that it's an infinitely large plate. And in practice, what that means is that the surface area is going to be much, much larger than the distance between the plates. And I suppose it's not really fair to compare an area to a distance, so I guess I would say the square root of the surface area is much, much larger than the distance. Now, as we saw back in lesson 5, we can calculate the electric field between two infinite parallel plates with a charge density of rho sub s on each one of them, and we get the equation 9.2 that's shown here. This was derived in one of the examples in lesson 5. But again, just remember that that's only true if you have infinite parallel plates. Later on in the course, we're going to talk about what imperfections are caused by the lack of this assumption, or what imperfections in the result are caused by us using this assumption. Now we know the charge density. The charge density is just the total charge Q divided by the surface area A on each of the two plates. So positive on the top one and negative on the bottom one. We also have an equation for the voltage between the two plates. V sub AB is the integral from A to B of E dot dl. Now in this case, the electric field is constant. Remember back up here, the electric field is constant in figure 9.2. And we know that it's constant because everything that's on the right-hand side of this equation is a constant. Rho sub s is a constant, epsilon 0 is a constant, so therefore E is a constant. Therefore, the E can be brought out in front of the integral, and then that leads us to just having E times D is the voltage. We can then plug those two equations in. Rho sub s times A gets plugged in for Q, and then rho sub s over epsilon 0 times D gets plugged in for E times D. So this part is E, and of course then that's just D. The rho sub s's are going to cancel. The epsilon 0 moves up into the numerator, and we're left with epsilon 0 times A divided by D. So we have a really solid equation for the capacitance of a parallel plate capacitor. If we do have a dielectric material in between the two plates, we're going to add an extra epsilon r. The only change from equation 9.6, I suppose. The only difference between these two equations is the epsilon r, and just remember that you can combine epsilon 0 times epsilon r and refer to them as epsilon. So that is the permittivity of free space, or the dielectric constant of free space, multiplied by the relative dielectric constant gives us, quote, the dielectric constant, epsilon. And notice that this result only depends on the geometry and the material that comprise the capacitor, that it doesn't have anything to do with the charge. We did have Q in the original definition, so here was Q in this equation right here. So this Q needed to cancel in some way with a Q that appeared in the denominator. And the way that we did that was we had a rho sub s in both the numerator and the denominator, and those rho sub s's canceled. If at the end of the calculation our result had shown either that there was a Q or a rho sub s anywhere in this final result, then we would have known that we'd made a mistake, because that can't appear in the final answer. Okay, so we're going to want to design a parallel plate capacitor. The surface area of each plate is predetermined to be 1 square centimeter. That's a pretty small capacitor. You know, you get these capacitors, but they're actually sort of twisted up and bound together very tightly, so that sometimes there's more surface area than you would expect. The space between the plates is filled with silicon dioxide, which has a relative dielectric constant of 3.9. If the capacitor must have a capacitance of at least 1 nanofarad, what is the allowable range for the distance between the plates? So the first thing I'm going to do is I'm going to convert 1 square centimeter by putting down here 100 centimeters and 1 meter, squaring that, canceling the square centimeters, and I'm left with 0.0001 square meter. And I also have the equation C is equal to epsilon 0 epsilon r times the surface area divided by the distance between the two plates. I know that my boundary case is that the capacitance must be at least 1 nanofarad is equal to epsilon 0, 8.854 times 10 to the minus 12th. Again, I don't need to write the units because as long as I'm consistent and use SI units in every step, they'll all work themselves out. This is multiplied by 3.9, and then that is multiplied by the surface area, which is 0.0001 square meters. And that's divided by D. I suppose I didn't need to write the square meters there. That was kind of the whole point that I made earlier. So I can now solve for D, and when I do solve for D, I get that it is 3.45 times 10 to the minus 6th meters, which is 3.45 microns. And that is the boundary case, but I was asked what is the allowable range for the distance between the plates. And just looking at this equation right here, we can see that as D goes down, C is going to go up. And we need that this capacitance be at least 1 nanofarad. So I'm willing to allow the capacitance to go up, which means that I'm willing to allow D to go down, which means that D must be less than or equal to 3.45 microns. It's a very small distance between those parallel plates. So we have a pretty small surface area and a relatively large amount of capacitance. We really do need to have that distance be pretty small. So that's stuff that you've already seen. You probably could have even already seen that in high school. But let's talk now about things that you may not have seen. We tend to think of capacitors as just being a pair of parallel plates, but you should be prepared to calculate the capacitance of other shapes. Especially at higher frequencies, these parasitic capacitances can make a big impact on the behavior of your system. Adding positive charges to any shape, regardless of its geometry or materials, will make it harder to move further positive charges onto that shape. It's true of things that have intentional capacitance, and it's also true of things that have parasitic or unintentional capacitance. When we want to calculate the parasitic capacitance of any shape, remember that you have to calculate the total charge on the shape and the voltage on the shape, both in terms of the same quantity. It could be that it's in terms of a rho sub S or a rho sub V, or it could be a rho sub L, or it could just be that you want to calculate both in terms of Q. So if you can find a function that lists V as a function of Q, then they'll naturally cancel each other out. So we're going to consider a couple of examples here. In both of these examples, we're going to use Gauss's law to calculate the electric field E, or D if there are dielectrics, then integrate that quantity over a distance to determine the voltage. So we're going to calculate E, and that E is going to either come from Q or from rho. One of those two is going to allow us to calculate E. From E, we're going to calculate V, and then from V, we're going to calculate C. That's kind of our workflow for each of these problems. Now, if you have only one conducting surface, for example, the next problem is going to be what happens if you have a metal sphere. There's only one surface there. There's one surface of the sphere. In that case, then you calculate the capacitance based on the absolute voltage of that surface. In other words, how hard would it be to move a charge from infinity and put it on the surface of that sphere? But if two separate conductors are involved, you use the voltage between them. So if you have, in the case of the parallel plate capacitor, how much would it take to move a charge from one plate to the other plate? Or if you have a coaxial cable, how much would it take to move a charge from the outside conductor to the inside conductor? So let's determine an expression for the capacitance of a hollow metallic sphere of radius A that has a total charge Q distributed across the surface of the sphere. How would this result change if the sphere were to be filled with a dielectric material with a relative dielectric constant epsilon r? So let's see a picture. Pictures are always good. I have this sphere, and it has a radius of A, and there is Q plus Q is distributed across that entire surface, and as a result of that, I have electric field lines propagating away from this sphere in the radial direction in each direction. So I can calculate the voltage. Well, I should also specify that the electric field, and we did derive this before, so you can go back into the earlier lesson where we first introduced the concept of electric field, is Q divided by 4 pi r squared. And that's true regardless of what the value of A is, as long as r is greater than A. So since we're going to be starting at infinity and working our way to the surface, we'll always be within the region where r is greater than A. So what is the voltage? The voltage is the integral from negative infinity up to A of E dot dl. And this is equal to the integral from negative infinity up to A of Q times A sub r divided by 4 pi epsilon 0 r squared. And then that's multiplied by, now we're moving from infinity to the surface. So that means that we're going in the negative A sub r direction, and we're moving with a dr motion. And so this turns out to be, I'll move out the negative Q over 4 pi epsilon 0. All of that moves out in front. And I'm going to have the integral of essentially, so these ARs are going to go away. The negative sign moved out in front. So I have a dr over r squared. And this becomes minus 1 over r, evaluated between infinity, or I guess you could say positive or negative infinity, up to A. So this becomes minus Q over 4 pi epsilon 0 times minus 1 over A, and then 1 over infinity is just 0. And this then becomes Q divided by 4 pi epsilon 0 times A. So the voltage on that surface is Q over 4 pi epsilon 0 times A, and the capacitance is equal to Q divided by V, which is Q divided by that expression we just found for the voltage, which is Q divided by 4 pi epsilon 0 times A. The Q's, of course, are going to have to cancel, and then the thing that's in the denominator of the denominator moves up into the numerator, so it becomes 4 pi epsilon 0 times A. And then the second part of the question is, what would happen if the sphere were filled with a dielectric material instead of being an empty sphere? And the answer is nothing is going to happen, because remember, all of the action took place out here. We had a charge that we moved from infinity all the way down to the surface. We never actually moved that charge into the surface of the sphere. So anything, don't know where that just went, anything that happens inside the sphere is really irrelevant. So epsilon r inside the sphere has no effect. And the reason for that is because the field exists, and so I'll say, since the field exists only outside the sphere. We know that there's no electric field inside of that sphere. That's one of the, if it's a hollow sphere, that's one of the results that we obtained previously from Gauss's law. So therefore, we know that if we're moving the charge only in the region where you're outside the sphere, no matter what happens inside the sphere, it won't make a difference. What would be the capacitance of a hollow conducting sphere of radius 1 meter? And then what about a sphere the size of the Earth, 6.37 times 10 to the 6th meters? So C, that is 1 meter, it's going to be 4 pi epsilon 0 times 1 meter, which is 4 times pi times 8.854, I had too many 8s in there, 8.854 times 10 to the minus 12th times 1, which is 111 picofarads. So imagine that you had a sphere that was 1 meter in radius. that is a very large sphere, and it has very small amount of capacitance. So these stray or unintentional or parasitic capacitances, you can imagine that if this were an even smaller sphere, something maybe the size of a millimeter, you can imagine that it would have an even correspondingly smaller amount of capacitance. And that's why often we can ignore it at normal frequencies, but if you get up into the gigahertz, even something in the attofarads is going to have an effect on the result. And then a capacitance of a sphere the size of the Earth will be 4 pi times 8.854 times 10 to the minus 12th times 6.37 times 10 to the 6th, and that works out to be about 709 microfarads. And so you can see that even a huge, massive sphere is going to have a relatively small amount of capacitance. Now let's talk a little bit about the capacitance of a coaxial cable. This one's actually going to make a bigger difference. When we start to talk about transmission lines, we're going to find that the capacitance and inductance of a coaxial cable impacts how quickly we can send signals over that coaxial cable, and that can have a big impact on things like digital communications, sending signals over coaxial cables. So let's first of all consider we've got an expression for the capacitance of a coaxial cable of length L that consists of a solid metal core of radius A surrounded by a hollow metal shell of radius B. So here's the picture. We have a solid metal core, and the radius of that one is A, and then we have a hollow concentric cylinder that has a radius of B. And the question is, what is the expression for the capacitance of this cable? By the way, it's not just a circle, it's a cylinder. Assume that there's a dielectric constant with a dielectric material with a relative dielectric constant epsilon r between the two cylinders. And so epsilon r exists in between them. We're going to go ahead and draw a Gaussian surface here. This is a result that we have already obtained, but I'm going to do it again, and I will call this rho. So that's the distance rho. And as long as rho is greater than A and less than B, that's going to be the region over which we're going to be doing our integral. So that then the question is, what is the electric field? Or more precisely, because we have a dielectric material here, we're going to be using the electric flux capacity, or the electric flux density. So that's D. So we have the surface integral, closed surface integral of D dot ds is equal to Q enclosed. That, of course, is the final form of Gauss's law in its integral form. Now, we know the surface area we know that the D is going to be constant because we've chosen the symmetry of the Gaussian surface to match the symmetry of the problem. So D can move in front of the integral, and this effectively becomes D times A. And the area of the cylinder, and just the side walls of the cylinder, not the two end caps, is equal to D times 2 pi rho times L. And that's equal to the enclosed charge. Well, the enclosed charge is going to be the charge that's on the inner cylinder. And we're going to go ahead and just say that that's equal to rho sub L. So because we don't really know any other information about the charge, we're going to call that rho sub L times L. So Q enclosed becomes rho sub L times L. We can cancel the L's here, and we're left with D times 2 pi rho is equal to rho sub L, and therefore D is equal to rho sub L over 2 pi rho. Remembering that rho sub L is the linear charge density, coulombs per meter, and rho is the radius in between those two. Now that we have the D, we can go ahead and calculate E. So E is going to be equal to D divided by epsilon 0 times epsilon r, which is rho sub L divided by 2 pi epsilon 0 epsilon r times rho, or we can just represent those two together as just epsilon. Remembering that epsilon is equal to epsilon 0 times epsilon r. Pretty soon now I'll just stop reminding you of that, but it's still worth reminding you of it for today. What is V sub AB? V sub AB is the integral from A to B of E dot dl. And the electric field is going to be, as we just saw, it's going to be rho sub, this is the integral from a to b of rho sub L divided by 2 pi epsilon rho, and then that's in the d rho direction. So the rho sub L, the 2 pi and the epsilon can all come out in front. So this is rho sub L over 2 pi epsilon. Those are all constants. And then the integral of, so I'll go ahead and write this one more time. A to b of d rho divided by rho. And that's one of my favorite integrals. So we get rho sub L over 2 pi epsilon times the natural log of rho evaluated between a and b. This turns out to be rho sub L over 2 pi epsilon natural log of b minus the natural log of a. Or rho sub L over 2 pi epsilon natural log of b divided by a. And so then finally the capacitance is equal to Q divided by V sub AB, which it turns out is rho sub L times L divided by rho sub L over 2 pi epsilon natural log of B over A. The rho sub L's cancel, and we're left with L times 2, and this is 2 pi epsilon is in the denominator of the denominator, so it's L times 2 pi epsilon divided by the natural log of B over A. Just double checking that that's the same answer. Yep, and then let me just give you a sort of one more real nice version of that. C is equal to 2 pi times epsilon 0 times epsilon r divided by the natural log of B divided by A multiplied by L. There will come some times in this class that we're going to want to know what is the capacitance per unit length. And it would be very convenient here to just say C hat, which is going to be the capacitance per unit length, is C divided by L, which is going to be, and I've kind of run out of space to put this, but 2 pi epsilon 0 epsilon r divided by the natural log of B divided by A. That'll be a result that will come back and be helpful to us in the last portion of this course. So we can calculate the parallel plate capacitor capacitance. We can calculate the capacitance of other geometries and calculate parasitic capacitances. We can calculate the capacitance of anything if we were given enough information about that thing and enough computational power. Now, if you look at a capacitor, you're typically going to see two numbers written on that capacitor. One of them is the capacitance, obviously, but the other one is usually a voltage. And that voltage is the breakdown voltage. It is the maximum voltage that the manufacturer guarantees will not damage the capacitor. And so, for example, if you see on the side of a capacitor, this is 47 microfarads, comma, 12 volts, or 33 microfarads, comma, 50 volts. That gives you information about the applications in which you could use that capacitor. And if at any moment you're going to exceed the voltage that is specified for that capacitor, then there's a good chance that you're going to damage the capacitor. So you might say, how can a voltage damage the capacitor? And the answer is no insulator is perfect. If you apply a high enough voltage to any insulator, it will eventually break down and it will allow current to flow. So you have the capacitor over here, and it's full of material that is going to resist the flow of current. And I'm going to have a voltage coming in here and a voltage coming out here. I guess that would be a current, but I'm going to say that this is maybe 1,000 volts, and this is going to be relative to ground. Well, what's going to happen is, just like a lightning strike, that voltage is going to work its way through this insulator and it will eventually strike down to the bottom. And the good news for gases and liquids is that if that happens, it'll usually be okay after you have removed the offending high voltage. Usually the gas will, whatever happened to the gas when it got oxidized or whatever whatever happened to it, it'll sort of circulate, new gas will be in its place and everything will be fine. And the same thing for liquid. But for solids, most typically, once something has been subject to a voltage that exceeds the breakdown voltage, it's permanently damaged. And a great example of this is an integrated circuit that has sort of a CMOS on it, that complementary metal oxide semiconductor. That oxide is an insulator. So the O in CMOS is going to be, or the O in MOSFET is going to be a capacitor that's going to, it's going to be an oxide that can be damaged by high voltage. And so if you have a little chip down here, and imagine that that chip is just sitting there, not hurting anybody, and then here comes this person's big finger, and that finger has a whole bunch of positive charges on it. Well, then as you touch, or even as you get close to it, zap, electricity is going to go from your finger into that chip, and there's a good chance that it's going to find its way into one of those oxides, and it will probably damage them, and it will be a permanent damage such as we saw over here on the left. So now we understand that, that if you apply a large enough voltage, it can cause the insulator or the dielectric to break down. The question is, how large is large enough? How large is so large that it would cause it to fail? And the answer is, of course, in an equation. In this case, it's an equation and a table. So we're going to, one thing that I want to mention to you is that everything we're about to talk about is oversimplified. Everything is a little bit more complicated than what we're talking about. I'm keeping the geometry extremely simple. I'm going to have an infinitely large parallel plate capacitor, and I'm simply going to say if I apply a certain amount of voltage between these two parallel plates, so here I have plus and minus, and I have a dielectric constant in between those two parallel plates. How much voltage would it take to cause a short circuit to zap between those two plates of the insulator? It's possible that you could have a geometry of the problem that would be more complicated than this, or a geometry that's going to have, maybe if you had a sharp point like this and a sharp point like this, that would be a different answer because the electric field lines would be very focused in this region, and those electric field lines can cause a discharge to occur very quickly. It's one of the reasons, by the way, why lightning likes to seek high, sharp points, like a lightning rod or like an antenna, is for just these reasons. So let's talk a little bit about these calculations then. We know that each material is going to have what we call the dielectric strength. And although I haven't actually seen a variable name used for this, I'm calling this E sub ds for dielectric strength. And I've got a table here which shows the dielectric strength of various types of insulators. It's not comprehensive, but it does give you a pretty good idea. And each one of these is in units of megavolts per meter. So although I don't list it here on each one of them, just know that these are all megavolts per meter. And so when you're looking these up, that's 10 to the 6th volts per meter. And so for air, you can see that it's 3 megavolts per meter. That means that if you wanted to have an electrical spark or an electrical arc that would go 1 meter, you would have to have 3 million volts to be able to do the jump of 1 meter. And that's good news. If you work in the electrical utility industry, that means that those arcs are going to take a lot of voltage to make that jump. The bad news is that it's not infinite. If you raise 3 million volts, you will find that the electrical arc will jump 1 meter. And again, I just want to emphasize that these dielectric strengths are best case. That quite often we're going to find that it will happen at a lower voltage. So it's usually a good idea for us to include a safety factor. Now these as I mentioned to you, these are electric fields. So these are electric fields. And as we know, voltage is electric field times distance. So whatever the electric field for the dielectric strength is, multiply that by the distance, and that will give you the breakdown voltage. So here the value of EDS is going to be the dielectric strength from table 9.1. The distance is the distance over which you're measuring that insulator, and then the breakdown voltage will be the product of those two. So what is the breakdown voltage for an electrolytic capacitor whose dielectric is 1 micron of aluminum oxide? Assume a 40% safety factor. So let's scroll back up here, and for aluminum oxide, we're going to see that it is 13.4 megavolts per meter. And so this calculation is actually pretty easy. VBR is equal to 13.4, and now it's not just units, it's not just the traditional units, so I'm going to be more careful about units. 13.4 megavolts per meter times, and it's 1 times 10 to the negative 6th meters. Well, the 10 to the negative 6 is going to cancel with the mega, and that therefore works out to be 13, and the meter cancels with meter, so I'm left with 13.4 volts. That would be an unusually small amount of, whoops, I forgot something, so I better erase that for a second. 13.4 volts would be unusually small, but we still have to assume this 40% safety factor. So VBR is actually going to be 13.4 times 1 minus 0.4. So a 40% safety factor, we're going to subtract that off the top, and we're left with 8.0 volts. Now that would be a very unusually small amount of breakdown voltage. Here's a capacitor. Don't ever get more than 8 volts on it. That could be problematic, but it is just an example problem. Here's another example. Most large electrical transformers, the sort that you see behind a chain link fence that are in typically a big green box, those are usually filled with oil because oil prevents arcing better than air does. And so we want to prevent arcing between nearby high voltage surfaces. Assume a transformer has 2 coils that are 10 centimeters, about 4 inches apart, and this space is filled with mineral oil. Using the most conservative value for the dielectric strength of mineral oil and including a 33% safety factor, what is the highest voltage difference that this transformer can safely accept? Okay, let's go back up and look in the dielectric strength table for mineral oil. We can see that it's 10 to 15, and so that is 3 to 5 times better than air. So you might say, well, is it worth it to fill it with mineral oil? Yeah, I think it really is. It does give you a lot better resistance to arcing. So we're going to take the conservative end of that, and we're going to say that it's going to be 10. So VBR is going to be EDS times D, which is going to be 10 megavolts per meter multiplied by 0.1 meters. 10 centimeters is a tenth of a meter, and that would give us 1 megavolt, 1 million volts. But VBR with the safety factor built in is equal to 1 megavolt times 1 minus 0.33, which it turns out is 0.67 megavolts or 670 kilovolts. So now we have a transformer, and if this were the only pair of coils that we needed to worry about for this, it could handle up to 670 kilovolts before there would be an arc inside that transformer. An average lightning bolt is approximately 5 miles long. Actually, let me adjust that. I think that it would be, I have some new information here. It's actually about 3 kilometers long. And so what voltage difference between the atmosphere and the ground would be necessary to create such a bolt? So VBR is going to be equal to E sub ds times D. And now we're faced with a question of what do we use for the dielectric strength? Well, it's air, so we're going to go ahead and tentatively use 3.0 megavolts per meter multiplied by D, which is 3,000 meters, 3 kilometers. The meters are going to cancel, and we're left with 9,000 megavolts, or 9,000 million volts, or 9 billion volts, or 9 gigavolts. All of those are the same answer. And so that would be our answer to how much voltage does it take to do this in an ideal circumstance. But remember, an ideal circumstance is where the air is still, it's calm, and the air is dry. So we're talking about, though, thunder and lightning, which is typically going to happen during an electrical storm. And in that case, the air is not still and the air is not dry. The air is wet. And so what we find is that not only do you have the water, the rain droplets, but also the humidity inside the air itself is going to dramatically affect this E sub ds quantity. And in reality, so the calculation that we did was valid given the inputs that we had, but in reality it's closer to 5% of this value, which is to say several hundred million volts. And that's because of humidity and rain. It seems crazy to be disappointed that it's only several hundred million volts. Maybe something like 3 to 400, 3 to 500 million volts would occur between the cloud and the earth. And that's what would cause the lightning bolt. It would not get up to 9 gigavolts because as soon as it reaches that threshold where it's going to have the breakdown voltage, then it's going to cause the lightning to strike. Okay, the last major topic for today is electrolytic capacitors. You're probably aware of two facts about electrolytic capacitors. First of all, electrolytic capacitors usually have more capacitance than other types of capacitors. If I told you that you needed 47 microfarads, you're not likely to reach for a ceramic disc capacitor. You're probably going to reach for an electrolytic capacitor because they have larger capacitances. We wonder why that would be, and we're going to talk about why that is. The second thing you probably know about electrolytic capacitors is that they are polarized. So you can represent that polarization either with a plus sign on one of the two terminals, or you can actually modify the symbol for the capacitor to indicate that it's polarized. One of the two plates is special, and if you put the capacitor in backwards, you're going to destroy it. And so the question is, why is that? So let's talk a little bit about that. I think that that's worth studying. Electrolytic capacitors are created, first of all, by using what's called an electrolyte. An electrolyte is either a liquid or a solid, which has a lot of electrical ions in it. And so the positive ions, called anions, and then the negative ions, called cations. This is very similar to a discussion that we could have about how electrical batteries work. That's kind of not within the scope of this course, but this idea of an electrolyte is an electrically conducting solution, either a liquid or a solid, that contains positive and negative ions. And when an electric field is applied, current flows through the conductor into the electrolyte, and then eventually into the other conductor. I'm going to skip down to the figure here so that we can see the picture that I think helps to illustrate this. We start out with a metal conductor, so this one is original, and we start out with an electrolyte, that one's original, and we start out with another metal conductor, that one's original. And notice that because the electrolyte conducts, and the electrolyte is right up against that right-hand negative metal conductor, this entire region, both the piece of aluminum and the electrolyte, is really one electrical contact. But when we apply a positive voltage to one side, what happens is the cations and the anions flow in such a way that they oxidize one of the two metal conductors. And they oxidize the one that's attached to the positive voltage. And so this is known as anodization. And this anodization is a way in which we can add coatings to different types of materials. And in particular, in this case, if we apply a positive voltage to one of the two terminals, we create this insulating layer right here. And that insulating layer separates two conductors, the conductor that was the original metal conductor here, and then the conductor that is the electrolyte right here. And so as you can see up here, I've drawn the symbol for a capacitor to show that it is that yellow insulating layer that creates the actual capacitance. We have a conductor on the left, which is aluminum, and a conductor on the right, which is electrolyte attached to aluminum. And this oxidizing layer can be made to be very thin. And because it is so thin, that's why electrolytic capacitors tend to have a higher capacitance than other types of capacitors. And then if you were to reverse the polarity, if you were to accidentally, or I suppose on purpose, put positive on the right and negative on the left, notice that then the action is going to be the opposite. And instead of building up that oxide, you're going to destroy the oxide. So when the manufacturer built and manufactured this electrolytic capacitor, they first of all built a sandwich of metal, electrolyte, metal. Then they applied a positive voltage to the positive terminal, and they allowed the oxide to build up naturally. And if you apply a positive voltage to the other side, you're going to slowly and eventually completely destroy that insulating layer. And of course, if you did that, it's just metal to electrolyte, which is a conductor, to metal, you're going to short circuit the capacitance. So if you apply the voltage in the wrong direction, you essentially make a short circuit that goes through that capacitor. So the capacitance is much higher because the oxide layer can be made to be very, very thin, and the capacitor is polarized such that one terminal must always be the positive terminal so that we don't accidentally destroy the insulating layer by de-anodizing it. So let's consider an electrolytic capacitor with aluminum conductors, and it has a surface area of 80 square centimeters and a breakdown voltage of 50 volts. The relative permittivity of aluminum oxide is 9.1. What is its capacitance? So we know that there were originally aluminum terminals. So this is aluminum, and this is aluminum, and in between there was an electrolyte. When we apply a positive voltage to this side relative to this side, aluminum oxide is going to form a layer right here, and we don't know how thick that layer is. But we do have a couple of other pieces of information. We know the relative, so we know the breakdown voltage, we know the relative permittivity, And we can also look up the dielectric strength of aluminum oxide. So let's look back up here. Let's find out what is that strength. Aluminum oxide, we saw that it was 13.4. So now we're going to come back down here, and given that 13.4, we're going to work backwards. We now know the breakdown voltage and we know the dielectric strength, but we need to find the distance. So V sub BR is equal to E sub DS times D, and therefore D is equal to 50 volts, the breakdown voltage, divided by 13.4 megavolts per meter, and this works out to be 3.73 microns. So now we know the distance, and we can now plug that into our equation for capacitance. It's epsilon 0, epsilon R times A divided by D. If you plug in everything that we know for each of those quantities, we end up with 173 nanofarads, or 0.173 microfarads. We'll use engineering notation, so this one's preferable. It's a little bit on the low side for an electrolytic capacitor, but maybe the surface area is a bit larger than we expected, or maybe one thing that the manufacturers do is they have ways of ensuring that the surface area is actually a little bit higher than what's expected by making that surface, rather than being totally smooth, they make the surface be a little bit rough. And so by having the surface be rough, they can actually increase the effective surface area of the capacitor. So, summary of what we've learned today. We know that capacitance is defined to be the Q divided by delta V. We have an equation for the capacitance of a parallel plate capacitor. We understand that all structures exhibit capacitance, and that in order to calculate that capacitance, we're going to go from some version of Q, which could include rho instead of Q. I'll say rho sub S. And that is going to be used to calculate the electric field. The electric field is going to be used to calculate the voltage, and then the voltage is used to calculate the capacitance. When you derive an expression for capacitance, the charge or charge density terms must cancel out, leaving only quantities related to geometry and materials. You can use this equation to calculate the breakdown voltage, or if you had another quantity, if you know the breakdown voltage, you can calculate either the material characteristics or the spacing. And then the electrolytic capacitors are formed by anodizing the aluminum that forms the anode, the positive terminal, that creates a thin insulating layer. But if you reverse the polarity of that voltage, you'll destroy that thin insulating layer.